We're doing extra practice problems for chapter 11. For number 1, we are supposed to identify the acid or the base. So we look at this side, and then we look at this side. This guy has gained a proton, hasn't it? So if this one gained a proton from here to here, then this is the base. Let's just check. Here we have 6 hydrogens. Here we have 5 hydrogens. So this guy donated a hydrogen ion, and therefore that is your base. You just look at how it's changed, remembering that an acid is a proton donator and a base is a proton receiver. Okay, so let's look at this one. From here, it has 2 hydrogens. Over here, it has 1 hydrogen. So this has donated a hydrogen. Let's look here. This went from C8H18 to C8H19. So this received the proton, so it is the base. So you just look at which one gave the proton, that'll be your acid, and which one received the proton, which is the hydrogen, and that will be your base. Number 2, HI is a strong enough acid that it'll make water act as a base. What is the chemical reaction between HI and water? Okay, we know that this is going to act as the acid, so it's going to give its hydrogen, its proton away, so we're going to make hydronium, and we were told that, weren't we? What's that going to leave of this? Strictly the iodide ion. And so that would be our balanced chemical equation for that reaction. If you do not include your charges, your answer is wrong. Remember, ions act differently than the particular elements that they come from. So you have to make sure that you have the charges there. Number 3, determine the reaction that occurs between the following chemicals. A, so the first one we have here is hydrochloric acid and ammonia. So we know that this is going to turn into the ammonium ion, and that's going to leave the chloride ion behind, and that is actually balanced. So that's the answer to our first one. Once again, the charges are imperative for the answer to be correct. We have an ionic hydroxide here. So an ionic base, we're going to make salt and water. So how many waters am I going to make? This one I have 2. This one I have 3. So what's the lowest common multiple? It's going to be 6. So I'm going to put a 3 in front of my 2. I'm going to put a 2 in front of my 3. And that would give me 6 waters. So I'm going to come over here and put my 6 waters. Now we deal with the salt that's left. I have aluminum, which is a +3. And I have, I'm pretty sure that's chromate, which we know is a -2, don't we? We know that because it's with 2 hydrogen ions. All right, and so now we're going to flip-flop our charges. This gets the 2, this gets the 3. And so now we're fully balanced. And then we get to C. Once again, we have a metal and a hydroxide, so this is an ionic base. We're going to make salt and water. You can look at this and know I'm going to make 3 waters, but I need 3 of these to make my 3 waters. So now I have my 3 waters, and what I'm left with is the sodium. And the phosphate, which you have memorized, is a -3, but you can always look at this and it tells you it's a -3. And so we have to flip-flop our charges, and so now we're balanced. And that's important, not only to do the equation, but make sure it's balanced or it's not done, and it's not correct unless it's balanced. Number 4, what volume of a 0.75 molar solution of hydrochloric will be required to neutralize 250 mils of a 0.01 molar solution of calcium hydroxide? So first, when you're doing these, write out your balanced chemical equation. Then you're going to put in your given and your get to so that you see what you're trying to accomplish. And so here we have hydrochloric plus we have calcium hydroxide. And so we look at this. This is an ionic hydroxide, therefore an ionic base. So we're going to make salt and water. You look at this and you go, I'm going to make 2 waters. So I need 2 of these. So I'm going to make my 2 waters. And then I'm going to have my calcium and my chloride ion. We'll flip-flop charges. And so make sure that you're balanced. And if you see you have your 2 waters, you have 2 chlorines, you have 1 calcium, you're balanced. Now we're going to add the information. It says what volume of a 0.75 molar solution of HCl, so 0.75 molar solution of this, and we're asked what volume, so we're going to put our question mark there, and would be required to neutralize. We have 250 mils of this, so I'm going to go ahead and put this as liters. It's 250 mils with 4 significant figures, and the concentration of this is 0.010 molar. Okay, now once again, everybody should be able to do that. You've balanced your equation, you've written in your given and your get to. You look at this and you say, here I have no question marks. Here I have a question mark. So I'm going to go through the mole tunnel. I'm going to get the moles of this, go through the mole tunnel to here, and then I'll be able to get my answer. So we start by going 0.010 moles per liter. That's what molarity is, times line. I have my liters. 0.0025 moles of calcium hydroxide. Now we're going to go through the mole tunnel from here to here. So I'm going to go times line, moles of calcium hydroxide, moles of hydrochloric. There's 2 hydrochlorics to every one of these. So that's going to give us 0.0050 moles of hydrochloric. Okay, and we want to know the liters. Well, we know that moles per whatever this liters is going to have to equal 0.75 molarity, which is moles per liter. So what we're going to do is multiply both sides by this, divide both sides by this. So I'm going to do that. 0.75 moles per liter. And so when we do that, notice the moles cancel and we'll be left with liters. That gives us 0.00, 2 significant figures, and I have 0.00666666, so we're going to go 7, and that would be liters because the moles cancel and I'm left with liters. So I've got my answer, 0.0067. So once again, write your equation. Make sure it's balanced, put in the given and the get to, figure out where you're going to start, go through the moles to get to where you're trying to end, to finish your answer. Number 5, a student needs to neutralize 550 mils of 5.6 molar sulfuric acid solution. How many grams of aluminum hydroxide should be used? Okay, so first, you're going to write your equation. First, you're going to breathe, you're going to pray, you're going to read it twice. Then you're going to write out your equation. So you do your chemical reaction. Now we're going to look at this. This is an ionic oxide, and therefore it's an ionic base. So we're going to make salt and water. We have 2 hydrogens here. We have 3 hydroxides here. The lowest common multiple is 6. And so we're going to put our 3 here, our 2 here. That way I'm making 6 waters. So I'll put my 6 waters here. I have aluminum here, and I have sulfate left over. We're going to flip-flop the charges. There we go. So now we're balanced. So far, so good. Now we're going to put in our information. It says a student needs to neutralize 550 mils of a 5.6. So we have 5.6 molar solution, and we want to neutralize 550 mils, 4 significant figures. How many grams of this do we need? Well, we know we're going to go from here through the moles to here, and then we can get to the grams very easily. So our moles are hidden in the molarity. Two significant figures. What comes out of my calculator is 3.08. So I'm going to make it 3.1. So that's moles, okay, of H2SO4. Now we're going to go through the mole tunnel. So I'm going to go like this, moles of the acid to moles of the base. There's a 2 in front of the aluminum hydroxide. There's a 3 in front of the sulfuric. And I need 2 significant figures, so it's 2.1 moles of aluminum hydroxide. And then I'm going to take my 2.1 moles of aluminum hydroxide. And I got moles of aluminum hydroxide here, grams of aluminum hydroxide here, and 1 mole, 78.01. Two significant figures. What comes out of my calculator is this, but I can't use that. I have to keep it to two significant figures. So the answer would be 160 grams of aluminum hydroxide, because I can only have two significant figures. So 160 grams. So you started where you had no question mark, went through the mole tunnel, and then you just went to grams. You can do this. You can do this. Let's see. Let's go to the next one. Number 6. 115 mils of a solution of HClO3 of unknown concentration is titrated with a 2.16 molar solution of sodium hydroxide. Tells us the volume of the sodium hydroxide to reach the endpoint. What's the concentration? Okay, of the HClO3. That's a C. There we go. And we're doing that with sodium hydroxide. Okay, this is an ionic base. It's going to make salt and water. I see 1 water. So that's going to give me the sodium and the chlorate. There's a chlorate and a chlorite, and I can't remember exactly which one that is, and I'm sorry. Okay, let's see. So we can take those charges away. We have a balanced chemical equation. All right, now we're going to put in the unknown. We have 115 mils of this, so I'm going to make that liters. 4 significant figures. Unknown concentration. And it's titrated against a 2.16 molar sodium hydroxide. And it takes 7.18 mils. So I'm going to go 718 liters. Yeah. Okay. So that's the information we're given. And we want to know the concentration of this. So we're going to start here, we're going to drive here. Thank God it's a 1-to-1 relationship, so the mole bridge will be easy. So the moles are hidden in the molarity, so I'm going to go 2.16 moles per liter times 0.00718 liters, and that will leave me with moles, 0.03 significant figures, 155 moles, and this is, this is of the sodium hydroxide, isn't it? Now, this is a 1-to-1 relationship, so if I go through the moles of sodium hydroxide to the moles of this acid, it's a 1-to-1 relationship, which means I'm going to be left with the same number of moles of the acid. So I'm going to bring that over here. And I want to know the molarity. Well, that's easy. I take the moles of the acid and I divide it by the liters, 3 significant figures and 4 significant figures, and 3 significant figures. This was 4,7, so I rolled it up. And that is the molarity of the acid in question. So that would be your answer. Once again, you're going to write your equation, make sure it's balanced, add your given and your get to, do it carefully so that you know that's in the right place, and then start working from where there aren't any question marks to where there are question marks, going through the moles. The stoichiometry will take you from one place to another. Okay, we're on number 7. A 1.34 molar solution of sulfuric acid is used to titrate 15 mils of potassium hydroxide. It takes 17.8 mils to reach the endpoint. What is the concentration of the base? Okay, so we have sulfuric acid, and we're adding to that potassium hydroxide. We look at this. This is a metal with a hydroxide, so this is an ionic base. We're going to make salt and water. How many waters? Look at it here. 2 waters. So I'm going to need 2 of these, aren't I? And there's my 2 waters. I know it's ugly. We're going to be left with potassium, which is a +1. And we're going to be left with sulfate, which is a -2. So there's the 2. We get rid of the charges, and we're balanced. That's your reaction, salt and water. And then we started with a 1.34 molar of sulfuric acid is used to titrate 15 mils. So I just moved the decimal place over 3 to make it my liters of solution. It takes 17.8 mils. That's 17.8 mils. That's how much it is in liters of acid to reach the endpoint. What is the concentration of the base? There it is. Okay, so we start where there's no question marks. 1.34 moles per liter times 0.0178 liters is going to give me the moles of sulfuric in 3 significant figures. This is 8.5, so I rolled it up to 9. The liters cancel, I'm left with moles, and this is moles of sulfuric acid. Now we have to get over to the potassium hydroxide. So I'm going to go like this and put the moles of sulfuric down here and the moles of potassium hydroxide up here. This gets a 2, this gets a 1. And so that's going to give me 0.0478 moles of potassium hydroxide. Okay, so now we're here. And I'm looking for the molarity. So if I have 0.0478 moles per 0.0150 liters, that's going to give me my concentration of the potassium hydroxide, isn't it? 3 significant figures. What comes out of my calculator is 3.186. So I'm going to put 3.19, and that's the molarity of the potassium hydroxide. 3.19 in 3 significant figures. Okay, just took the moles that we found of the potassium hydroxide and divided it by the liters that was given. Number 8, concentrated acetic acid is 17.4 molar. How would you make 750 mils of a 1.5 molar acetic acid solution from concentrated acetic acid? Well, we know that M1V1 equals M2V2. And the concentrate is the first one. It's where you're starting. So I'm going to put that in, 17.4 molar. How would you make, so we're going to, looking at the volume, that's what we're looking for. 750 mils, so that's my new volume. 750 mils of a 1.5 molar. There you go. So this is your final molarity, your final volume. This is your starting volume, and so you're solving for how much of it will you need and then dilute it in water. And so you just take these 2 numbers and divide it by that one. Now I want you to notice what I did was I divided both sides by 17.4 molar. When I do that, my molarity will leave. The answer that comes out of my calculator, I need 2 significant figures, is 64.65. I'm going to just show you, 64.65, blah, 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 blah. I need 2 significant figures, so this is going to be 65, and what's left is mils. So my answer, I don't have to convert this to liters because it'll just give me an answer in milliliters. So my answer is 65 milliliters of the concentrated acid plus whatever I need to get up to 750. So I'm going to go 750 minus 65 plus 685.0 mils of water. Or you could just say 65 mils and then add water until it gets to 750 mils. You are welcome to do that. Now, when I did number 8 my way, M1V1 equals M2V2, because of significant figures, I got a different answer than he did. My answer was 65 mils. His answer is 63 mils, and it's because of him doing it the other way. So let's do it his way too. So we're going to figure out the moles of the second one. And so the moles of the second one, in this case, would be 1.5 moles per liter. And we're told how many mils that are used. And so that's going to give me two significant figures, 1.1 moles of acetic acid in that secondary solution. And so in the primary solution, we started with 17.4 moles per liter, and we want to get to 1.1 moles, so we need to know how many liters of that to use to get there. So we know that that times this number of liters times what number of liters will give me 1.1 moles. There we go. And so we are going to divide both sides by this, and that will do it for us, because if we divide both sides by 17.4 moles per liter, we'll be left with liters. So we go 1.1 divided by 17.4 equals, yes, and that gives you the 63 milliliters. Three significant figures, that or 63.0 milliliters. Now, I told you when we do it the other way, we got 65, and it's because we took two significant figures here. The other way is more exact because you're doing it all in one step, so you're not taking significant figures as you went. So either number would be acceptable. And that's where you're going to have a little discrepancy in his answers and mine, depending on which way you chose to do it. But if you have the right number of significant figures and you did the work correctly, then it's right. I just want to make sure you're aware of that. Okay, let's do the next one. The next one is number 9. A chemist makes 50 mils of an acetic acid solution with a concentration of 5 molar. A student wants to use that to make a 1.5 molar solution. What volume of 5 molar solution can he make if he uses all of the original solution? Okay, so he makes 50 mils of acetic acid solution with a concentration. So we have 5.0 molar acetic acid, and we have 50 mils of it. And a student wants to use it to make a 1.5 molar solution. There we go. So we want to know what volume of this we have to use to make this. All right, so let's go to the moles. Let's go to the moles. So we have 5.0 moles per liter times, we're going to make this liters. Three significant figures. Okay, so that's going to give us, and that's moles. Okay, so we have 0.25 moles of acetic acid. Now here it says that what volume of 5 molar solution can he make if he uses all of the original solution? And so we have this, so we go 0.25 moles divided by how many liters would give me a 1.5 molar solution. There you go. And so we're going to divide both sides by 1.5, multiply both sides by liters, because this is actually moles per liter, right? So that's going to give me liters. And so when we do that in two significant figures, it gives me 0.17 liters, because it's 0.16666, so that's going to be 0.17 liters. Now let's try that the other way. Okay, so chemist makes, this is the original, 50 mils of a 5.0 molar solution, and we know that we want to make as much as we can of a 1.5 molar, and we want to know how many liters. So I'm just going to put V2. So we know we're going to divide both sides by 1.5 molar. And so that's going to give us 50 times 5 divided by 1.5, and two significant figures. In two significant figures, it gives me 170 mils, which is exactly the answer we got the other way. So we can use this one. Sometimes the significant figures will give us a slightly different answer, but not all of the time. So now you've seen it both ways. I think this one's easier, but that's just me. Number 10, a chemistry student takes 50 mils of sodium hydroxide solution, dilutes it, now has a volume of 250 mils. He then titrates 250 ml solution to find it's a 1.7 molar. What is the concentration of the original 50 ml solution? We're looking for the original solution. We used 50 mils. We dilute it to the new volume of 250 mils, and the solution to find it is 1.7 molar. There we go. So we are solving for the original volume. So we're going to divide both sides by 50 mils. That's going to get our volume by itself. And we need two significant figures, 8.5 molar. My calculator gives me 8.5 molar. His answer is 8.6 molar. I'm sure it's got to do with the significant figures again and how he went through it. Either answer would be acceptable. You have the two significant figures. And we just did it slightly differently. Okay, I hope that's a help. Let's go ahead and do it the other way. If we did it the other way, we're given the molarity of the second molarity, which is 1.7 moles per liter, and we're given how much we have of it, which is 250 milliliters. So I'm going to go 0.25, and that 0 is not a significant figure, liters. And so that's going to give me two significant figures, 1.7 times 0.25 equals 0. Now, this is what I get in my calculator. But I can't use that, can I? So I'm going to take this and roll up to 3. Okay, there's my moles of the secondary one. And we are told that of the first one, but we're looking for the molarity of the first one, but we're told that we used 50 mils. So if we have 0.43 moles divided by 0.0500 liters, that gives us 8.6 molarity. 8.6 molarity. Now, once again, it's got to be taking the significant figures right here that makes that minor change. You do it either way, it'll be correct. Okay? It's up to you. But just make sure you have the right number of significant figures, and we'll take into account that slight change. All right? Guys, we're on chapter 11. We've only got, what? We've got 16 in the book, so we have 5 to go. You're doing a great job. Just keep up the good work and be encouraged. Study all of these. Make sure you're comfortable with it. Take your test. Show all your work so that if you've got a slightly different answer, I can look at it and tell it's okay. Have a Jesus-filled week.